Hello everyone, I'm Liu Yang. Before we start the computer lab, I will first introduce you a game called Snakes and Ladders. Snakes and Ladders is played on a numbered board where players take turns rolling a die to move their token forward. If a player lands on the bottom of a ladder, they move up to the top. If they land on a snake's head, they slide down to its tail. The first player to reach the final square wins the game. It is important to note that the game requires no skill because players have no control over the outcome of the die rolls, which dictate movement. Additionally, the interactions with snakes and ladders are predetermined, meaning players cannot influence their path. Therefore, this game is completely based on chance. This piece of pseudocode is designed to simulate the snakes and ladders game through the function playGame, which takes a game board model and a winning square number n. It initializes the player's position at 0, which is outside the board, and sets up a loop that continues while the game is ongoing. In each turn, the algorithm rolls a die, updates the position, and checks if it has reached or passed the winning square. If so, a win message is displayed and the game ends. If not, the code checks for ladders and snakes, where ladders move the player up by adding values to their position, and snakes slide them down by subtracting values from their position. Each turn concludes with outputting the current state, and the game continues until a win occurs. Finally, the function returns the total number of moves taken to win. In this example, the algorithm first rolled a die, received an outcome of 2 and moved to square 2, which it then found a ladder and moved to square 12. In its second move, the algorithm received a die outcome of 3 and moved to square 15. The algorithm then rolled a 4, moved to square 19 and found a snake that moved it back to square 10. In the fourth move, the algorithm rolled a 4 and moved to square 14, and it rolled another 4 in its fifth move, which brought it to square 18. Finally, the algorithm rolled a 6 in its sixth move and win the game. The notation Pm equals m represents the probability when m, the random variable in this experiment, which is the number of moves needed to win the game, is equal to a specific value m, and p is the probability mass function. The probability of winning the snakes and ladders game within a specific number of moves can be estimated by simulation as it counts the percentage of games that are won in that specific number of moves in a number of simulations. More specifically, a simulation can be considered as a success if win in the number of moves that the user wants to test. The probability can then be calculated by dividing the number of successful outcomes by the total simulations, providing a statistical estimate of winning chances for different move counts. The simulation was then implemented in Python version 3.12.4, but with a more complicated game board. The board is modeled by first generating a list of 101 zeros, with the zeros index representing off the board and the 100th index representing the last box of the board. Values were then changed in indices that have snakes and ladders, in which the snake is represented as a negative value and the ladder is represented by a positive value. The playGame function manages and prints the player's movements based on die rolls and the effects of ladders and snakes, returning the number of moves taken to win in the end. The PMF function estimates the probability of winning in a specified number of moves by running simulations and counting successful outcomes, then dividing the number of successful outcomes by the number of simulations. 3 additional functions were then designed to plot the graph. The first function, GenerateList, simulates a specified number of snakes and ladders games. It calls the playGame function for each simulation, which returns the number of moves needed to win. These raw results are collected in moveList, which is then returned. The second function, sortList, takes the raw list of moves and creates a new list consisting of each unique value of move counts that occurred during the simulations. It checks each move from the raw data to avoid duplicates, then sorts this list in ascending order before returning it. The third function, PMFList, computes the probability mass function for each unique move number. It counts how many times each unique move count appears in the raw data, calculates the probability by dividing the count by the total number of simulations, and appends these probabilities to another list that is being returned in the end. Finally, the code imported the matplotlib library to create a bar graph. The plt.bar function takes in 2 arguments, categories, which are the unique move counts, and values, which are their corresponding probabilities. plt.xlabel, plt.ylabel, and plt.title are then used to label the x and y axis and give a title to the graph. As we can see in this graph generated from 1 million simulations, it is the most common to win the game in 9 moves, and most games are won in around 10 to 20 moves, with the probability dropping off as the number of moves increases. The long tail on the right indicates that while most games are completed quickly, some can take significantly longer due to unlucky encounters with snakes.